Alright, so in this video we are going to learn about MLIR, the new compiler that is basically the foundation of a new programming language called Mojo. Since the main designer is Chris Ladner, if he's best known for his work on LLVM, which led to languages like Rust and Swift. And basically, if you use an iPhone, you use Swift everywhere. Before that, there used to be Objective C, but after Swift and LLVM, also if you're on Mac, if you try to compile, the default compiler for C language is Clang, which is written C-lang, but it's called Clang. So we are going to learn about this compiler, and we are going to read the paper from Google Research. I have a version of this already open, but yes. Alright, so MLIR scaling compiler infrastructure. We can just make this one scale smaller. Doesn't let me. It's interesting. I don't know why it's not letting me scale this, but oh, here we go. I feel like this is much better. Alright, so abstract. This work presents MLIR, a novel approach to building reusable and extensive compiler infrastructure. MLIR addresses software fragmentation, compilation for heterogeneous hardware, significantly reducing the cost of building domain-specific compilers and connecting existing compilers together. MLIR facilitates the design and implementation of code generators, translators, and optimizers at different levels of abstracting and across application domains, hardware targets, and execution environments. The contribution of this work includes 1. Discussion of MLIR as a research artifact built for extension and evolution, while identifying the challenges and opportunity posed by this novel design. Semantics, optimization specification, system and engineering. 2nd, evaluation of MLIR as a generalized infrastructure that reduces the cost of building compilers, describing diverse use cases to show research and educational opportunities for future programming languages, compilers, execution environments, and compiler architecture. The paper also presents the rationale for MLIR, its original design principle, and structures and semantics. Alright. Introduction. Compiler design is a mature field with applications to code generation, static analysis, and more. The field has seen the development of a number of mature technology platforms which have enabled massive reuse, including systems like the LLVM compiler, the Java virtual machine, and many others. A common characteristic of these popular systems is their one-size-fits-all approach, a single abstraction level to interface with the system. The LLVM intermediate representation is roughly C with vectors, and JVM provides an object-oriented type system with a garbage collector abstraction. This one-size-fits-all approach is incredibly valuable, and in practice, the mapping to these domains from ubiquitous source languages C and C++ and Java respectively is straightforward. At the same time, many problems are better modeled at a higher or lower level abstraction. Example, source level analysis. of C++ code is very difficult on LLVM So many problems are better modeled at a higher or lower level abstraction. Example is source level analysis. So if I can just bring my notes so we can take a few notes, that would be great. So source, let me just go to the next line. Source level analysis. Okay. Of C++ code is very difficult on LLVM intermediate representation. We observed that many languages, including examples like Swift, Rust, Julia, Fortran, develop their own IRR in order to solve domain-specific problems, like language library-specific optimizations, flow-sensitive type checking for linear types, and to improve the implementation of the lowering process. Similarly, machine learning systems typically use ML graphs as the domain-specific abstraction in the same way. While the development of domain-specific IRs is a well-studied art, their engineering and implementation cost remains high. The quality of the infrastructure is not always a first priority or easy to justify. For implementers of these systems, consequently, this can lead to lower quality compiler systems, including user-visible problems like slow compile time, buggy implementation, suboptimal diagnostic quality, poor debugging experience for optimized code, etc. MLIR project aims to directly tackle these programming language design and implementation challenges by making a chip to define and introduce new abstraction levels. Alright, so let's take a break there. So basically, I feel like what they're doing is they're introducing these abstraction levels, so you as a person probably can configure or choose the way your compiler optimize your code, and basically optimize the way your machine language models are run. That's just my first assumption. And provide in-the-box infrastructure to solve common compiler engineering problems. MLIR does this by first standardizing the static single assignment based IR data structure. So MLIR abstraction. I cannot make notes bigger. Why Apple? Oh, can't use Notion, but that's for next time. Okay. First is standardizing the static single assignment SSA base intermediate representation data structures. Second, providing declarative system for defining IR dialects. And third is providing a wide range of common infrastructure, including documentation and parsing and printing logic, application tracking, multi-threaded compilation, support, pass management, etc. This paper further presents the overarching principles underlying the design and implementation of MLIR. We will explore the essential design points of the system and how they relate to the overarching arcane principles, sharing their experience applying MLIR to a number of compilation problems. Contributions. Most of MLIR system is built out of well-known concepts and algorithms, yet the objectives and designs are sufficiently novel that studying them offers vast opportunity for research, and even more so within the boundaries of the following overarching principles. Parsimony, apply outcomes related to built-in semantics, concept, and programming interfaces. Harness both intrinsic and incidental complexity by abstracting properties of operations and types. Specify invariants once, but verify correctness throughout. Query properties in the context of a given compilation path with very little built-in. This opens the door to extensibility and customization. So, okay, I don't like this. Okay, I don't think Apple likes that. Like, all right, I'm gonna use Notion. New tab. We call it MLIR. What are we doing? Screen MLIR. Just bring it here. Alright. Okay, so Occam's razor. Just gonna have some key points. Parsimony. Occam's razor to built-in semantics. Traceability. Retain rather than recover information. Retain rather than recover information. Declare rules and properties to enable transformation rather than stepwise imperative specification. Extensibility comes with generic means to trace information enforced by extensive verification. Composable abstractions stem from glassboxing their properties and separating their rules, types, control, data flow, etc. Progressivity. Premature lowering is the root of all evil. Beyond representation layers. Multiple transformation paths that lower in. Yes, one of the reasons we switched to notions that could be seen better. Individual regions on demand. Together with abstraction, independent principles, and interfaces, this enables reuse across multiple domains. While these principles are well established, one of them is often implemented at the expense of another. Layering in network and operating system stack aligns with the progressivity principle but breaks parsimony. Alright, so premature lowering is the root of all. Beyond representation layer allow multiple transformation paths that lower individual regions on demand. Together with abstraction independent principles and interfaces, this enables reuse across multiple domains. Alright, in a nutshell, we identified design and engineering principles for compiler construction to thrive in a narrow middle that support an open semantics ecosystem. We discover complexity can be tamed without restricting expressivity, allowing for fast IR design exploration and consolidation across domains, both of which are severely lacking in production systems. The contributions of this paper are 1. Positioning the problem of building scalable and modular compiler systems in terms of proven design and engineering principles, A description of a novel compiler infrastructure that follows these principles with important industrial and research applications. Exploration of select application to diverse domains illustrated the generality of the approach and sharing experience developing systems that build on the MLIR infrastructure. So basically they gave us three: parsimony, traceability, progressivity. And so this kind of trilemma that you can find in blockchain, and from there they are basically saying layering in network and operating system stacks aligns with the progressivity but breaks parsimony. I don't quite understand this, but I believe if we make a few searches we can figure it out. Okay, work on MLIR began with the realization that modern machine learning frameworks are composed of many different compilers, graph technology, and runtime systems, which did not share common infrastructure or design principles. This manifested in multiple user-visible ways, including poor error messages, failures in edge cases, unpredictable performance, and difficulty generalizing the stack to support new hardware. We soon realized that the compiler industry as a whole has a similar problem. Existing systems like LLVM are very successful at unifying and integrating work across a range of different languages, but high-level languages often end up building their own high-level IR and reinventing the same kind of technology for higher levels of abstraction. At the same time, the LLVM community struggled with the representation of parallel constructs and had to share front-end lowering infrastructure for C-calling conventions or cross-language features like OpenMP, with no satisfactory solutions. Faced with this challenge, given we could not afford to implement and improve compiler instances, we decided to go for a more general solution, investing in a high-quality infrastructure which would benefit multiple domains. Progressively upgrading existing systems, making it easier to tackle pressing problems like heterogeneous compilation for specialized accelerators, and provide new research opportunity. Now that we gathered a significant amount of experience building and deploying MLIR based systems, we are able to look back on its rationale and design and discuss why this direction was pursued. Alright. So basically makes sense. They're saying this new technology is trying to be a generalization that many languages probably need, and instead of just adding features to all of them, MLIR try to give the tools to have these features implemented for all of them. Alright, so let's move to the design principles. Let us now explore the requirements that guided the design of MLIR and their relation with the overarching principles. Little built-in, everything customizable. Little built-in, okay, so that's probably the definition of parsimony. I didn't Google search this, but little built-in, everything is customizable. Specify invariance once, but verify correctness throughout core properties in the context of a given compilation path. With very little built-in, this opens the door to extensibility and customization. Alright. This looks good, okay. A handful of abstractions, types, operations, and attributes, which are the most common in IRs, should be used to express everything else, allowing fewer and more consistent abstractions that are easy to comprehend, extend, and adopt. Broadly, customizability ensures the system can adapt to changing requirements and is more likely to be applicable to future problems. In that sense, we ought to build an IR as a rich infrastructure with reusable components and programming abstractions supporting the syntax and semantics of its intermediate language. A success criterion for customization is the possibility to express a diverse set of abstraction, including machine learning graphs, ASTs, mathematical abstractions such as a polyhedral. Right, so we have new vocabulary, AST and polyhedral. Polyhedral control flow graphs and instruction level IRs such as LVMIR, all without hard coding concepts from these abstractions into the system. Certainly, customizability creates a risk of internal fragmentation due to poorly compatible abstractions. While there is unlikely a purely technical solution, the system should encourage one to design reusable abstractions and assume they will be used outside of their initial scope. SSA and regions. Seems to be still part of the customizability. Let's just roll back to parsimony. Query properties in the context of a given compilation path with very little built in. This opens the door to extensible. Yeah, okay. Okay, now I just clicked. So they go to the network layers and operating system stacks, and they said those things are not that parsimonial. I take parsimonial. As a widely used representation in compiler IRs, it provides numerous advantages, including making data flow analysis simple and sparse. Is widely understood by the compiler community for its relation with continuation passing style and is established in major frameworks. As a result, the IR enforces the value-based semantics of SSA. Static single assignment. Its referential transparency and algorithmic efficiency are considered essential to a modern compiler infrastructure. However, while many existing IRs use a flat linearized CFG, let's have it written. CFG. I don't know why this happened, but okay, much better. Representing higher level abstractions push introducing nested regions as a first class concept in the IR. This goes beyond the traditional region formation to lift higher level abstractions, loop trees, speeding up the compilation process, or extracting instruction or SIMD parallelization. To support heterogeneous compilation, the system has to support the expression of structured control flow, concurrency constructs, closures in source languages, and many other purposes. One specific challenge is to make CFG-based analysis and transformations composed over nested regions. Okay, so we want to have nested regions. In doing so, we agreed to sacrifice the normalization and sometimes the canonicalization properties of LLVM. Being able to lower a variety of data and control structure into a smaller collection of normalized representations is key to keeping compiler complexity under control. The canonical loop structure with its pre-header header latch body is a prototypical case of a linearized control flow representation of a variety of loop constructs in front-end languages. We aim at offering users at a choice. Depending on the compilation algorithm of interest of the paths in the compilation flow, nested loops may be captured as nested regions or as linearized control flow. By offering such a choice, we depart from the normalization only orientation of LLVM while retaining the ability to deal with higher level abstractions when it matters. In turn, leveraging such choices raises questions about how to control the normalization of abstractions, which is the purpose of the next paragraph. Okay, to be honest, I'm a little bit lost, so these are very big words. All of them seem to me to be buzzwords. But I feel like the only way that we can understand this better, we can just keep going. Alright. Maintain higher level semantics. Okay, so from proximity, what's it even called? Proximity? Parsimony. From parsimony we go to proximity. Okay. From proximity we need to go to traceability. Parsimony, traceability, proximity. Okay. Maintain higher level semantics. The system needs to retain this information and structure that are required for analysis or optimization performance. Attempts to recover abstract semantics once lowered are fragile, and shoehorning this information at low level often invasive. Example, all passes need to be revisited in the case of using debug information to record structure. Instead, the system should maintain the structure of computations and progressively lower to the hardware abstraction. The loss of structure is then conscious and happens only where the structure is no longer needed to match the underlying execution model. For example, the system should preserve the structured control flow, such as loop structure, throughout the relevant transformations. Removing this structure in an example lowering to a CFG essentially means no further transformation will be performed that exploits the structure. The state of the art in modeling parallel computing constructs in a production compiler highlights how difficult the task may be in general. Alright. This was a heavy paragraph. Attempts to recover abstract semantics once lowered are fragile, and shoehorning this information at low level often invasive. All passes need to be revisited in the case of using debug information to record the structure. As a corollary, mixing different levels of abstraction and different concepts in the same IR is a key to allowing a part of the representation to remain in higher level abstraction, while another part is lower. This would enable, for instance, a compiler for a custom accelerator to reuse some higher level structure and abstractions defined by the system alongside with primitive scalar/vector instructions specific to the accelerator. Alright. Let's take a look. Have a break for now because I'm losing my voice. Okay, Okay, so let's just figure out what these are. Abstract syntax tree. Polyhedral math. Oh, interesting. Three-dimensional object or solid is formed using 4 or more polygons or 2-dimensional shapes. Right, that's fair, my understanding. Let's just take a look at one of these. So let's just give me an example. So we have like goals and expression, term, factor, term, expression, term. Alright, okay, so this is like after the pre-processing is done, your analysis part is done, then I feel like you have a abstract syntax tree. Right. Alright, let's go back. Continue with this. Another corollary is that the system should support progressive lowering from the high level representation down to the lowest level of performance, small steps, allowing multiple abstractions. The need for multiple levels of abstraction stems from the variety of platforms and program models the compiler infrastructure has to support. Previous compilers have been introducing multiple fixed levels of abstraction in their pipeline. Example is the Open64 virl representation has 5 levels, as does the clam compiler, which lowers from abstract search trees to MLIR to selection directed graph, if I'm not wrong. Directed acyclic, so a directed without any loops graph, acyclic graph, 2 machine instruction and 2 MC instruction. More flexible designs are required to support extensibility. This has deep implications on the phase ordering of transformations. As compiler experts started implementing more and more transformation passes, complex interactions between these passes started appearing. It was shown early on that combining optimization passes allowed the compiler to discover more facts about the program. One of the first illustrations of the benefits of combining passes was to mix constant propagation, value numbering, and unreachable code elimination. Okay, so let's just finish this and then we go for a scan, because at this point I feel like we need some analysis on what we read. We need to find out the relationships of what we read, try to reflect on it a little bit. So let's just finish that page and then we can just go over everything once, what we read. Or maybe we need a little bit more understanding of compilers in general and LLVM. So we are going to do that as well. Okay, so declaration and validation, parsimony and traceability, no proximity. Parsimony and traceability, no proximity. Defining representation modifiers should be as simple as introducing no abstractions. A compiler infrastructure is only as good as the transformations it supports. Common transformations should be implementable as rewrite rules expressed declaratively in a machine analyzable format to reason about properties of the rewrites, such as complexity and compilation. Rewriting systems have been studied. Rewriting systems have been studied extensively for their soundness, efficiency, and applied to numerous compilation problems, from type systems to instruction selection. Since we aim for unprecedented extensibility and incremental lowering capabilities, this opens numerous avenues for modern program transformation as rewrite systems. If I have it drawn, it will be better. Okay, so we're here. So the best way to understand this is probably writing a baby language. Like, if I'm not wrong, I saw this that you could write a toy language. Polyhead. Yeah. And then see how that goes. Okay. So we write systems. Also raises interesting questions about how to represent the rewrite rules and strategies, and how to build machine descriptions capable of studying rewriting strategies through multiple levels of abstraction. The system needs to address these questions while preserving extensibility and enforcing monotony and reproducible behavior. Alright, so this makes sense. You want to have reproducible and deterministic behavior from your compiler. That's understandable, but what I don't know is when you don't want to have deterministic behavior. Okay, so let's search that. Maybe we can use perplexity. I'm going American. Behavior from compiler. Here we go. Nothing causes this to occur. Undefined behavior cannot occur. Just the question. What is the phrase undefined behavior? Someone published compiler. When would you want to use a compiler? Alright, so it seems to be a thing. Non-determinism. Oh, interesting. So there are functionalities like these. We can make this bigger so see it better. I've identified three main causes of a non-deterministic behavior in C++ compiler. Iteration of unordered containers, hashing of pointer keys, and use of non-stable sort functions. Oh, I should know what non-stable sort functions are. I see. So in an unstable sorting algorithm, the data is stored so that the order of elements with equal keys is not preserved after sorting. Alright. I feel like quick sort and heap sort and selection sort. Why selection sort is... Oh yeah, because in selection sort you just swap two values, and that's probably why the sort is unstable. But does that make the thing? But if you have like a selection sort, and maybe not for selection sort, but if you're running selection sort, every time you run the selection sort, the unstability of the sort causes non-deterministic compilation. That needs more thinking on my side. Yeah. Okay. The system needs to address these questions while preserving extensibility and enforcing monotonic and reproducible behavior. The openness of the ecosystem also calls for an extensive validation mechanism. While verification and testing are useful to detect compiler bugs and to capture IR invariance, the need for robust validation methodologies and tools is amplified in an extensible system. The mechanism should aim to make this easy to define as declarative as practical and providing a single source of truth. A long-term goal would be to reproduce the successes of translation, validation, and modern approaches to compiler testing, both for currently open problems in the context of an extensible compiler. Alright, I'm going to stop recording. I'm gonna come back with the second part. It's going to just explain these 3 pages that we read and then continue from there. So thank you for watching this, and I will see you in the next part.